In the previous lecture we were discussing about the Reynolds transport theorem, its derivation and its contextual relevance to mass conservation or the continuity equation. We will move forward from there and we will try to discuss a couple of examples to illustrate the use of Reynolds transport theorem for conservation of mass. So the first example is you have a plate the length of the plate is L and this plate is coming down with a uniform velocity V naught. There is a fixed boundary and this plate is approaching the fixed boundary. In between the plate and the fixed boundary there is some fluid with constant density . And when this plate is coming down, the fluid is getting squeezed out radially from both the sides and it is given that the velocity profile at the outlet is given by u is equal to some where h is the gap between the two plates which itself is a function of time. So the objective is to find out from here the relationship between h and time, that is h as a function of time. What is that? This is the first objective. Given that at t is equal to 0, h is equal to h0 and then what is the relationship between u0 and v0? This velocity v0 is uniform. So in this way this problem could be formed with several parameters known, several parameters unknown. The question is that what is the basic principle that we apply? The first part is very straightforward and for that we actually apply the common sense principle that you have dh dt is equal to minus V0 because at time equal to 0 h is equal to h0. So integrating this you will get this one. So this is h as a function of time. For the next part we have to relate this motion with the flow which is going radially outwards. To do that we can make a control volume analysis. So let us make a control volume like this. And in this control volume let us assume that the sides of the control volume, the edges of the control volume constitute a geometrical dimension which does not change, that means this is a non-deformable control volume. So this whatever you have drawn, this remains like this. So if it remains like this, then the plate which is coming at the bottom from the top coming towards the bottom, it will result in some flow of the fluid across the face of the control volume. There could be another possibility in which this control volume would move with the plate, then the difference would be that the volume of the control volume will change with time. In this case the volume of the control volume is not changing with time. So if the volume of the control volume is not changing with time, so what we will do is we will consider the two possible scenarios. One is a control volume like this which is fixed, another is a control volume which is moving with the plate. Drawing wise they will not look different, because I mean you cannot draw a moving control volume dynamically in a static picture, but we have to imagine the two cases differently. So the first method we will consider that fixed control volume. So if you apply the mass conservation, okay. So if it is a fixed control volume and rho is constant, then this term is 0, this term is always 0 because a control mass system will always have a fixed mass. So what is that? This particular term will have one inflow and another outflow. For inflow the dot product of the vector and velocity vector and outward normal vector is negative, and for outflow it is positive. So this will be minus V0 into L by 2, let us say B is the width of the plate, into B, this is inflow, and outflow integral okay. So this will give you a relationship between U0 and V0, because this U will be, now you can substitute this expression here, right, there is a rho here, right. So both terms rho rho, and this is equal to 0. So conceptually it is the rate at which the fluid is flowing in is the rate at which the fluid is flowing out if rho is not variable. That is the basic paradigm that we are considering here. Let us just for the sake of fun say consider another method. Yes, oh sorry, 0 to h, sorry, this is inertia of writing all the time, L by 2, okay, this is h, yes, 0 to h, right. Okay, now just for the sake of fun we will consider another method, method 2. Method 2 is control volume moving with the plate. So drawing wise it will look similar, but imagine now that as the plate is moving down, this is shrinking, this dotted box is shrinking in size. So dm dt this term, the first term is always 0. Now because the volume of the control volume is changing with time, this term will be non-zero. So what will be this term? So assuming rho to be uniform, this will be just ordinary derivative d dt of rho into L by 2 into B into H, right, and here there will be only outflow but no inflow, because the control volume is moving with the plate relative to the control volume, there is no net flow which is flowing in, right. So it will be just rho right. Look at this term, rho is fixed, L by 2 is fixed, so rho into L by 2 into B, and dH dt is minus V0, right. So you look into these two, the formulation is the same, the final answer is the same. So this is where you have to train your student to work out a problem in different approaches. It is not getting the answer that is always important, but the approach that is being used. In one case a deformable control volume, in another case a fixed control volume, but those approaches are converging to the same final result. That impression must be created in the mind of the student, and I think that is a very important job for control volume analysis. Another important point that you must hammer in the mind of your student is that whenever you are doing a control volume analysis, typically using Reynolds transport theorem, the control volume must be specified partly by drawing and partly by words. Otherwise you see this is the control volume for both the methods, right, but by words only we can describe their difference, in one case deformable and in another case not. So that clarity must be there, and that clarity is very important to relate what the student is writing with what control volume he or she has taken, and that should be one very important component of your assessment rather than just making an assessment on the final answer. Okay. So, we have worked out a maybe simple but representative case of conservation of mass. Next we will do conservation of linear momentum. So, conservation of linear momentum will essentially talk about the Reynolds transport theorem applied for linear momentum. In that way, first we write the Reynolds transport theorem. It is always the best, you know, to start with the most basic equation and then go on applying it for the specific problem or the specific case, then your chance of making mistake will be only algebraic, but conceptually you will not make any mistake. So, dn dt of the system okay. So, n in some junior classes we write this n as just mv. I mean conceptually it is mv, but fundamentally it is this, because the fluid is continuously deforming, every elemental mass may have its own velocity. So, it is not that the entire system is having a common velocity. That is why this integral form is the more fundamental way of writing it, although if you write it as mv, I mean nothing is, I mean not that sky is falling on your head, but you have to keep it in mind that this is what you essentially mean. So, small n is this per unit mass, so this becomes the local V. So, d dt of integral dmv, sorry this is system, system or control volume depending on this or this, so better not to write anything here. So, d dt of dmv system okay. Why in this manner we are writing is the simple fact that we cannot write this as a force, but we can write this as a force, because the Newton's second law is applicable for a control mass system. So, this is the resultant force acting on the system. By Newton's second law, this becomes resultant force which is acting on the control volume as well. The reason is that we have derived the Reynolds transport theorem in the limit as delta t tends to 0, the time interval tends to 0. As the time interval tends to 0, this system will tend to the control volume. So, this is the expression for the Reynolds transport theorem for conservation of linear momentum. Let us work out an example. let us say that there is a solid boundary and fluid is coming from far stream with a velocity, uniform velocity u infinity. The length of the plate up to which you are doing the analysis is L. Because of viscous interaction between the fluid and the solid boundary, there will be a region close to the solid boundary where a velocity profile will be created, a velocity variation will be created. This region is called as boundary layer. So let us say that at this location you have the boundary layer thickness as delta. So the velocity profile here is given by u infinity question is that what is the force exerted by the fluid on the plate? Okay. So this equation tells us nothing but the rate of change of linear momentum because of two things. One is linear momentum change within the control volume plus a linear momentum flux out and in, balance of that gives rise to the net force. So the net force is because of, so if it was a control mass system, the net force would be because of the rate of change of linear momentum of the system. Here because it is control volume, so there is also a flux of momentum coming in and going out, and that adds to the net force. Sometimes this is called as momentum theorem. So in fluid mechanics, in various texts, typically in the undergraduate level this is not derived and this is just introduced as a momentum theorem in most of the undergraduate fluid mechanics textbooks, but I believe that Reynolds transport theorem being the most general one, no matter whether it is mass, momentum or whatever conservation, it is better to follow from that, and I do not mind if this is called as momentum theorem, but it is fundamentally Reynolds transport theorem applied for momentum conservation. Next what we will do, we will make a choice of the control volume. Now let me make a clear simple choice first and see what is the demerit of this choice. So if you make a choice like this, which is a rectangular box, the problem is that there is some mass flow across this also. The reason is that whatever is the mass coming in here, less than that mass is leaving here because there is a velocity profile. So to make up for that, the remaining mass should go out of this so that total mass is conserved and there is no accumulation if the density is constant. So density is constant is our assumption, I am not writing it over again and again, but density is constant is a major assumption. So then that will add to the calculation of momentum flux, because if some mass leaves here, it will carry certain momentum along with it. So what can be the choice of the control volume instead of this, which will result in no flux of mass? That choice is nothing but a streamline connecting these two, because by definition streamline, this is not the edge of the boundary layer. This is a conceptual mistake that the students make. There is a difference between this streamline that we are drawing and edge of the boundary layer. What will be the, how will the edge of the boundary layer look, we will discuss about that when we talk about boundary layer theory. But this is essentially a streamline. So because it is a streamline and we say that there is no net flux across it, so we can write the mass conservation with this unknown being sorted out. If this height is h naught, which you do not know, because you have, what you have done, you have made a geometric construction, you have passed the streamline through this point. Now naturally wherever it will cut it, it will cut. This is not a given problem parameter. So you have to find it out by noting that again dm dt so this is 0 because the control volume is fixed and rho is fixed, this is also 0. So this will have one inflow and one outflow term. So inflow is minus u infinity into h naught and outflow is integral u dy. So this becomes a governing equation for h naught, which is integral u by u infinity dy. Remember this is flow rate per unit width, so width is taken as 1, width of the plate. Finally we will apply this momentum balance. So the resultant force, rho is fixed, v is also not a function of time, so this term is 0. So next term it will be, so one is outflow, so integral rho u square f per unit width, this is outflow, minus this is inflow. So u into u and outflow being plus and inflow being minus. Okay. Now in place of h naught you can write u by u infinity dy from there, integral 0 to delta. So f by width rho is constant, you can express it in a simple way by dividing both the sides by rho u infinity square, just normalize it. So it will be integral u by u infinity into u by u infinity minus 1 dy, and this u by u infinity as a function of y by delta is given as, you can substitute, and the limit 0 to delta, if you change y to y by delta, it will become 0 to 1, and then you can integrate this very easily. So you can clearly see that the answer of this should be negative, because u by u infinity is less than 1. Why the answer should be negative? So this is the force on what? This is the force on the control volume, that means force exerted by the plate on the fluid. Because the plate has a dragging effect or slowing down effect, it will have a force in the negative x direction. By Newton's third law, the force exerted by fluid on the plate will be minus of F. That will be your answer. So whenever the question is asked, you have to make your student careful whether it is asked to find out force exerted by the fluid on the solid boundary or solid boundary on the fluid. Depending on that, proper algebraic sign has to be worked out. These are finer details, but these talk about the concepts in understanding the subject. Thank you very much. We will continue from here in the next lecture.